Hello everyone, my name is Viraj and today we'll be looking at the 7th problem from the CP-31 sheet by TLE Eliminators under the 1000 rated problems. Let's go. So moved on to my sheet over here, ticked off 1000 rated and let's go to the 7th problem, array merging. Let's open this up. You are given two arrays A and B, both of length n. You will merge these array forming another array C of length 2 into n. You have to find the maximum length of a sub-array consisting of equal values across all such C arrays that could have been obtained. Now they have defined merging. How does merging happen? Merge of two arrays results in array C composed by successively taking the first element of either array as long as that array is now empty and removing it. After this step, the element is appended to the back of C and we repeat this operation as long as we can. Alright, okay, let us quickly generalize this problem. Very simple. You will start off with a variable n and two arrays of this size. Let's call this array A, array B. Let's say they have the numbers A1, A2, A3, A4, A5, so on till An. And then you have the array B, B1, B2, B3, B4, B5, so on till Bn. Now you have to create an array C. What is the procedure to do that? You start picking up one element from the start of any of this array, whatever your choice is. Let's say I pick up A1 and I'll move this A1 over here. So now the array has elements from A2 onwards. Then let's say maybe I pick up A2 and then I move it over here. So basically I keep appending A1. Then let's say A2. You can say A1 is gone, A2 is gone. Now let's say I pick up B1. This is the first element now in B and move it over here. B1 is gone. Then let's say I pick up B2. Okay. Then let's say I pick up B3. Let's say B3 is here. Then let's say I pick up A3. So A3 is here and so on, so on, so on. So can you see the pattern that I'm doing? I'm picking up the first element from either A and B and I'm trying to append that back to C. Now this sort of method that I'm doing is of course going to create an array C, which is total going to have a length 2 into n. Why 2 into n? Because n elements from here, n elements from here. So of course 2 into n is the total size of this array. Yes. Now the idea is there can be many different iterations of C, right? So if all different type of C arrays can come or can be obtained, what is the thing that we want finally? We want that we do such an optimal sort of merging of the C array such that if we try to figure out the, you can say, length of a sub array of C after operations have been done, consisting of all equal values, as in you find a subarray which has all the numbers equal. You want this length, let's say I'll call this length L, to be as large as possible. You want the max length of that subarray. This is the question. Let's quickly understand this with some random case. Okay, so let's say the array A was 1, 2, 3, 3, 3, 5, 5. Let's say the array B was 1, 1, 2, 3, 3, 3, and then let's say 5. And then let's say even 4, maybe something like this. So now what is the answer according to me? Carefully see. What I can do is I can create an array that looks like this. Let's say I'll pick up the first two elements. So I'll first insert this 1, then 2. Then the next three elements, let's say. So this is 1, 1, 2. Then these three, right now, 3, 3, 3. Then these next three, okay, 3, 3, 3. When I'm saying these next two, next three, I basically mean 1, 1, 1, 1 at a time. So I think you can imagine that part. Let's say these next two 5, so 5 and 5. And then let's say this 5 and 4. So I can say 5 and 4. Now, if I ask you what's the answer, see over here. Can you see this subarray? Has a total size of 6, has all the values equal, and the argument is this is actually the max possible. Try to see if you can do something better than this. Pause the video, see for yourself in this test case. You might not be able to come up. If you quickly run this idea once more in the test case, let's say test case number 5. So the array is 1, 2, 2, 2, 2, and then this is 2, 1, 1, 1, 1. So one of the best optimal approach in this case would be, let's say I pick up this one element, I keep it over here. Then let's say this two element and I keep it over here. Then let's say this, all these four elements continuously from the array A. So 2, 2, 2, 2, 2 again. And then this 1, 1, 1. So 1, 1, 1, 1, 1 again. I think we have to remove the last one. So sorry. Yes. Now tell me, what do you think is the best answer? Look at this subarray. Very neat. Subarray of size 5, all equal values. Best case, yes, 5 is the answer. Alright, so I hope the question is clear. You have to just imagine how are you merging the elements from A and B one by one by one and pushing back in C, and you get the best possible answer, finding the best length of a subarray having everything equal. Alright, great. I think we have understood the question. We have understood the test cases. You can pause the video, run this simulation once more on these cases, although they are very easy. Try to figure out something of your own, try to come up with some idea, and then let's start actually discussing the problem. So before we proceed further, we need to understand what sort of a time complexity are we looking for. Yes. So I can see that test has 1 second given to me, although it has been told that in that test, that is the sum of n doesn't exceed for all test cases. So I can directly have a comparison with this n factor being 10 raised to 5 order. Given that 1 second is allowed for one test, that basically means 10 power 8 number of operations, and n given in, you can say 2 into 10 raised to 5 order. What am I looking for? I can create solutions that look like something O of n log n, even like O of n square root of n might even work. But then anything after that, above that, let's say I create a solution that looks like O of n square, or I even start going above that, that's not going to work because n is 2 into 10 raised to 5 order. 10 raised to 5 order square is of course going to exceed this. So in this order, till constant, everything is right. I mean, I can tick off boxes over here. All of this is seamlessly going to work, but this is a problem. And this is a very good discussion on our expected time complexity, because now I have a rough idea that I'm not looking for a brute solution. I'm not looking for something that might work in n square, and I'm looking for something below that. All right, great. Now, since we have already discussed that we don't want something like an n square, my question to you would be, do you think you want to actually simulate this process? Do you think you actually want the array A and B to be there, and let's say you actually create some array C and then try and keep on pushing back in the array C and so forth, so forth, and so forth, and so on? Do you actually want something like this? I don't think you do that. Why? Because if you do this, you actually keep on merging from one half to other half to other half. You have a lot of possibilities to explore, right? How many different possibilities will you check? How many different C arrays can you actually create? Physically, that's not right. Which means I need to come up with a smarter idea. To be very specific, now that I know I'm not trying to come up with C actually, that means I need some algorithm by which I can first of all decide how would the best C array look like? How would the best C array look like? And if I'm able to decide that yes, this is the best C array that will look like, then I know I can just calculate the answer maybe very, very quickly. Great. So I hope this is a good starting point. This is a good intuition. One observation. Second observation or second intuition is we are looking for some value which dominates or becomes the equal value in a single subarray. So let's just assume something over here. Let's say that that value is x. Now imagine in your first array, I have something that looks like this. Let's say the array A looks like this. I'll use dashes for all the elements that are not x, and let's see what happens. So x, something like dash, dash. Then let's say you have x, x, x. Then let's say dash, dash. Let's say x, x. Then let's say dash, dash. This is array B. Now this is array B. Let's say x, 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 x. Then let's say dash, dash, x, dash, dash, x, x. Let's say dash, dash, dash. Let's say this is array B. So basically what I've done is I have marked everything that is that x element. This is the x element. Now, first of all, the argument stands. You basically want that when you merge these two arrays, the largest subarray of x joins together. Let's look at a very greedy based idea. Tell me, isn't this intuitive that if I want this block of x in this C array to be as large as possible, I would prefer that I look at the largest current subarray of x in A also and in B also. Meaning, if I ask you, there is a subarray over here that is of 3 size, which has x. There is of 2 size, which has x. Now, just for A, if I ask you, which is a better subarray to prefer or to use, will you say this one or will you say this one? It's of course better to go with this one because this has more x's. Next point. If I talk about this, there are 4 x's over here continuously, 1x, then 2x. What should I prefer? I should of course prefer this part. This has 4 x's. Now when I'm saying I should prefer this, prefer that, and I'm losing the other part, if I try to imagine this very carefully, when I do the merging and I try to prefer that I take a segment, I can actually make sure that those two preferred segments from A and from B actually come together. Meaning, I can always argue that this segment of length 3 and this segment of length 4 can actually join by very smart sort of a merging so that they together give me 3 plus 4, a 7-lengthed segment. Let's see how that is possible. Let's say this is the orange color left half. This is the leftover right half. Technically, I'm not bothered with the left and the right half. I'm only bothered with the green portion, that is the largest one. And let's say this is all that is there in the right half. Left part is of course standing. Now, I'll give you a very simple idea. If I want that this green and this green come together so that the subarray expands, can I do a very smart idea? Can I pick up this much orange portion and let's bring it over here. Let's do this with color. Some orange portion will come from here belonging from A, you can say left. Okay. Now, let's bring up this green over here and then right next to it, that green over there. Let's do that. So this is the green that comes from the left part, sorry, A. This is the green that comes from the B then. Okay. Now let's continue. Let's pick up this orange part, for example, or maybe this, doesn't matter. Let's say I pick up the orange part from B first. So B right, you can say, I pick up. And then finally, I place the A right orange portion also. And voila, see this. Isn't the largest portion of X from A and the largest portion of X from B actually joined together? Can you say that if this length was 3 and this length was 4, you added that and that became 7? And isn't that greedily the best? Of course, I wanted this value to go as large as possible, which individually meant I can increase this as well as this. So that is what I did. I first of all preferred that I take the largest one in A. So I took, let's say the options were to take 3 or 2 or other. I took the preferred case, I took 3. And when I said about B, I did the same thing. I preferred that I take the 4 guy, not the 1-lengthed or the 2-lengthed segment. And I hence maximized the taking from B, that was 4. Now, if A was also maximized greedily, B was also maximized greedily, I of course made them join together, overall making my answer the most optimal subarray I could have gotten of continuous length, you can say, highest length, you can say, containing all X values. Now, I did this with X. Let's go back in the constraints once more. We can see that the elements are from 1 to 2 into n. Similarly, in the B array also, the elements are 1 to 2 into n. And n is not very large. N is 2 into 10 raised to 5 order. Which means the elements in the array, this X range that I'm talking about is from 1 to 2 into 10 raised to 5 order. So if I figure out the largest subarray length for each element from 1 to 2 into 10 raised to 5 in A, similarly, I'll figure out the largest subarray length or longest subarray length, whatever you call that, from 1 to 2 into 10 raised to 5 order in the array B, and then for every element from 1 into 10 raised to 2 into 10 raised to 5 order, I can just add up their answers. I can say that AI or AX plus BX gets added up, and that gives me the best possible subarray. So you can say answer basically becomes the max of all A of X plus B of X, where you can say A of X is the longest subarray length of all X values. Similarly, B of X, like this is in A array, is the longest, same thing, length of all X values in B array. I hope this is clear. I hope this makes sense. Let's go back once more and look at the cases that I actually discussed with you and see how does that work. So what would have happened over here is, in this case that I showed you, I would have first calculated and asked you what's the longest for each. So I would have said, okay, for like, I'll talk about the array A right now. So in the array A, I would have said that 1 has the longest subarray as 1, 2 has again 1, then I think 3 has, you can say 3, and 5 has 2. Then over here in B, I would have said, okay, 1 has 2, 2 has 1, then 3 has 6, and then 5 has 1, and 4 has 1 also. So now I would have asked you, okay, let's go to individually each and every value and see. So I went to asking for 1. When I say I take this value, let's add that with this. That's the longest subarray in B having all values 1. Let's add this up. This becomes 3. Similarly, let's add this part up. What do you get over here? This is 1 plus 1. This is 2. Then this is, okay, I think I wrote this wrong. 3 has 3 over here. Okay. Then if I add this up, this becomes 6. Then add this up, this becomes 3. And if I add this up, technically this becomes simply 1, because over here you could have imagined that 4 was not even visible in the array A. So you can say 4 had 0 mapping. So this becomes 0 plus 1. This is 1. Now what's the maximum out of this? Of course, the maximum is 6. And isn't 6 the answer? Yes, 6 was the answer. And how did we create 6? That's the argument. How did we do that? We took the idea that I told you. I can mark it again with orange. I said this had been the orange region that we would have picked up. Okay. And can you see? This is the orange region, then this is the orange region, and this part was the orange region. And this part was actually the region of all threes, which I actually combined together. Great. Let's take one more test case. I think I can clear one more idea over here, which I feel might get skipped out. Let's say array A has something like 1, 1, 2, 2, then let's say 3, then 2, 2, 2. And then let's say B array has, let's say 1, 2, 2, 2, 2, and then let's say 3, 3. Now, I want to take the longest subarray length from A for a number. So if I ask you, what would that have been in A and B? Let's note this down. For 1, this is 2. Yes, you can see 2 subarray longest. What about 2? Option is this also, option is this also. So what would you take? You would take 3. For 3, you would take 1. Now, let's talk about B. Over here, 1 has 1, 2 has 4, and 3 has 2. Same thing, let's add. This becomes 1 plus 2, this is 3, this is 4 plus 3, this is 7, and this is 2 plus 1, this is 3. What's the max? Max is 7, and yes, 7 is the answer. Now, how do I get 7? I would have said, this is completely a green part, okay? Or not a green part, you can say orange part, which I want to keep initially. Then this is an orange part, this is an orange part, and the rest part is the green part, which I want to merge. So I would have placed all the orange initially, as an orange from here, place it, okay? And then the green portions, let's bring the green portions together, green, and then let's finally bring this orange portion back. And yes, voila, overall 7 achieved. Now, this also clears up one more doubt, is that you might think, is it possible for us to actually merge the segment of 2, specifically in this, from the same array? Like, could I have taken this also into picture? It's not possible. Why? Because if you try to very clearly imagine over here, you would have to place this 1, 1 first. So let's say you place 1, 1. And then you would have to place, let's say this one over here. So you place this one. Now, as soon as you place these 4 2s, so 2, 2, 2, 2, and then if you place this one, so this is like 2, 2 more, now there would be a break. This is actually the break point. Yes, this becomes a breakpoint, that is 3. So now if you want to use these 3 2s again, there would be a breakpoint in between. So for a same array, that is why I mentioned in the very start only when I put an argument that from a single array, let's say either from A, either from B, for a single element X, I'm not trying to consider the other segments that fall. I just want that segment that's the highest possible, because other segments cannot be utilized any further. So this is a very diagrammatic question. I feel I have covered one test case of that type, one test case of this type. You can make your own test cases, run this idea through these test cases also that were given over here. And I think that's going to give you a clearer picture of why this merging is happening in this way. This is the most optimum, of course, and if I want to greedily better my idea, it's always best to go with the largest in A, largest in B for individually every element, and let's do this for everything so I can maximize my overall answer with all such different answers that pop up. Great. So I think we have understood the whole problem. Now, how do I implement this? Implementing this is going to be very, very simple. There is a very classic idea that we normally bring in practice when we want to calculate something on a sub array. Okay, and this is very classic, you can say, question of where you want right now to calculate the overall length for a continuous block of sub array. this technique is called counting and reset technique, or you can say pointer technique, whatever you call that. I like to call this counting and reset technique. What we can do, we can maintain a counter. Let's say it starts with 1, that is the one subarray that we start with. Then let's say a for loop that goes. Now if I feel that the element at the ith location is, let's say, equal to the previous location also, for example, then counter increases, because then I know that I am basically maintaining a continuous block of that particular element. Elements are same, previous element is also same, so it continues C++. Else, if this condition is not true, then I go in the else block and I know I have broken now. I know I am at a place where I need a break. So if I need a break, I need to reset C equals to 1. But before I reset, whatever this C value is, I can take the C value and maximize the C value that currently stores, let's say, that if the number was AI, what's the largest continuous block that we found right now, that is C. So let's maximize this. You can say something like your array name as, let's say, long A, something like that. So long A of I is equal to max of that value itself and C. This is like a rough pseudocode that I've written. It's a very simple logic, count and reset. No need to discuss this in very depth. You can pause the video and you can search this up as clear as day. I will do this, as I mentioned, I'm going to do this for the array A. I do the same repeated code for the array B, and then all I would want to do is run a loop from 1 to elements are, let's say, 2 into n till 2 into n, and just figure out A of I, B of I, add this up, and of all such possibilities, max out. Whatever is the answer, it's the max of all such AI plus BI values. Great. So let us jump at the code part quickly. Just how I explain the pseudocode. I think code is going to look much more neater as we go over here. Yes, we have the element n, take the input of n, and the array A, take the input of that, array B, take the input of that. Now I have a longest sub-array A vector. Why a vector? I could have also used, so because I'm trying to maximize the values and I'm trying to store them at a particular location, I could have used any data structure that helps me to do that. I could have done a map, I could have done a vector, because vector might also give me a good estimation on how I want to store. I prefer to use a vector over here. You can of course use any different data structure to store these values. I will name this as longest subarray A, where what I'll do is I'll say every ith index basically means that if the number was I, what is the maximum or the longest subarray in A for that element I. So indexes should be from 0 to overall I want 2 into n plus 1 length, so that I get the index till 2 into n. Everything starts with 0. Same thing goes with B. I do the same thing over here. Then I have this counting and reset technique. I have a counter, starts with 1. I start with the first element, as in first index element, not 0, because counter is initially 1. So I know the first element has been counted. I start with the first index element or the second element indirectly. Now, if A of I is equal to the previous element, that means a continuous block is continuing. You can imagine it's going from like left to right. It's okay. It's equal. Go expand, count more. And then as soon as I break, if this is not equal, that means I have broken. Now I'm starting at an AI element, which is not equal to the previous. So there's a break between that. There has been a shift of elements. You can imagine. So I know I need to reset my counter, but before that, I need to make sure that I actually store this C value and compare this with the A of I minus 1 to get maximum value. So longest subarray A of I minus 1. A of I minus 1, why? Because this counter value is basically trying to store the, or would have stored exactly, the longest subarray possible for the A of I minus 1 value. So I'll say longest subarray A of I minus 1. Let's call that index, and at that location maximize that same value with this counter variable. And when I come out of this for loop, I'll do this line once more. Why? Because I need that overall when I end this for loop, maybe I don't go in the else check once more. So this is just for the safe side, that the very end when I exit the array, the last continuous block that is there also needs to be compared and stored well. Where that will be stored, A of n minus 1 maximize with itself and whatever is that counter value. Now once this part is done, I do the reset of counter to 1 and I do the same idea for B. You can say the code is literally copy pasted. And then once this is done, I have basically achieved what I wanted in all these test cases that I showed you. This pink column that I drew. Let's say for this test case, this pink column would have come. Let's say for this test case, the pink column would have come, and so forth. So this pink column would have generated very, very easily for me. This one, this pink column over here. So I would now just want to get the best AI plus BI value. So let's take a max frequency variable. That's the answer. Let's start with -1 for all the elements. So from 1 to 2 into n less than equal to 2 into n, maximize this variable with longest subarray of A of I plus longest subarray of B of I. Okay, and let's print this at the very, very end. Great. So now what is the time complexity? We have sort of like an n order over here to take the input. You can say n order over here input, n order over here, then vector will initialize a 2 into n order. So that's like 2 into n, roughly n order again. This is n order again, maximizing n order again. This is like n order again. Then this is like 2 into n order again. So which is roughly equal to like n order only. So I can say that the time complexity that I've achieved is actually O of n. And O of n is very good. Why? Because we wanted something like O of n actually when we started off our discussion of expected time complexity. So this is like 2 into 10 raised to 5 order. And space is also O into 2 into, like, it's O of 2 into n because I have 2 extra vectors over here. But then 2 into n is also roughly n only. So you can say 2 into 10 raised to 5 order once more. This is like a rough order over here that I've estimated. Okay. So this is all that is there in the problem. Very, very fun problem. Has tweaks of little concepts. This counting and reset is a technique. How did I store this is also a technique, by the way, right? You could have done this with a map also. So different implementations to the same problem can happen. The crux idea should remain same. You should first of all be very clear of this merging part that is happening, the greedy merging that is happening. We always want to take up the largest possible for a specific element in A and largest same for B and try to club that together. And to do that, I showed you a very simple technique of this diagrammatic way of orange and green distribution, whatever you call that. I hope that helps. And this is the idea. All right, so that is all that is there in the problem. I hope you like it. Thank you for watching.